Yeah, that's a little bit down the road, I think, as far as that. Yeah, let's see. Actually, there we go. So, okay, so in the section there, 12.3, torsional shear stress. And I thought I had. Okay, so note what my notes say is using figure 12C. So that's this. Let's go back here and get rid of all this gobbledygook here. See if we can erase all that ink on the slide. And I'd really like that to be bigger. So if we were looking at 12.2C, that's the one on the bottom, right? That situation develops pure shear stress. There's no bending or direct tensile or compressive stress on that. By the way, I didn't take any points off on that first problem on the quiz for not putting tension. That force was tension. I didn't even count it at all. So, but it should have been a tensile stress, right? I mean, when you're pulling something, yeah, when you're pulling something, it's in tension. That's all I wanted.
And the instructions say
to say what it was, to declare it. Yeah.
So extra credit for that part?
No.
I put it on there. For it.
I might go back. I might give you an extra credit for that. Yeah. If you've got it on there, which I pretty much know who did. Put your pen down. Okay. So if we look at that, again, note that that's strictly pure shear stress. There's no tension or there's nothing pulling that shaft or compressing that shaft. It's strictly tension on the torque, if you will, from that perspective. It's pure shear stress. There's no bending or direct tension or compression on that. The internal resistance to the slippage of the material or the deformation is known as torsional shear stress. And note that all materials have a limited shear strength. And so we're going to have to develop a relationship between the torsional shear stress, torque, and the material's physical properties. So if we look at this figure 12.6 here, some things are going to apply here. So it says when an external torque is applied, there's a shift in the plane occurs, and that's what we're showing here, this shift in this plane. So it tweaks that plane a little bit, doesn't it? The plane still exists, and it stays that same size, if you will, and the radius from O to D is the same as the radius from O to D prime. Okay? In other words, that doesn't change. Now, when it fails, it's probably going to change. Okay? But up to that failure point, no change. Fair enough? So we can create some kind of relationship there. So assuming the stresses stay below that proportional limit, that's where I was talking about, when it starts to fail, when it starts to deform, all bets are off. Okay, and the material conforms to the Hooke's law, which is the stress proportional to the strain law. Then the shear stress at a location on the line EF will be equal to half. I use some shorthand here. Equal to half of the shear stress developed on the outer surface. So the shear stress developed in torsionally loaded circular shafts is proportional to the distance from the longitudinal axis of the member. Okay, so in other words, we can predict, so if we go, in fact, I may be a step ahead of myself, but the torsional shear along this line EF here is going to be half of what it is at CD. Okay, so, or if you were looking at that from an end view, In fact, we can go to this. It'll be something like that. So the shear, the torsional shear, goes down, if you will, the closer you get to the center. Okay, and it's a proportional. It's a linear proportional amount there, as shown by that triangular shape. So you can predict that a little bit better. Okay, depending on where you're at on that shaft.
So the distance between R is the same as the distance between O and F in the previous.
Let's see. Okay, so the distance. Well, that's
distance R in that picture is the same as the distance F in the previous slide.
I don't know that we can say that, because that distance R is going to be. What they're using that to say that R could be any number, but it's going to be a proportional amount. They're using that in the next, actually in the equation. There's an equation that's going to show that.
Okay.
So basically that R, and then they're going to tie that to an area. It's one of those infinitesimally small areas, that they're going to be able to move that anywhere and predict what the stress is going to be. So that's what they're looking at there. Actually, it would be just half of C in that picture would be what that EF was.
Okay.
So EF in the previous picture was right here as a point.
Yeah.
Okay. But it would be showing up as a point in this. This is the end view of that shaft, isn't it? Okay. So that's what they're telling us on that. So it would be half of the shear as half as much as it would be out at point D. And that's what that picture with all the that's a distributed load, right? If you will, but graduated down. And again, once we get to the center or to the axis of the part, there's no shear stress. There's no torsional shear in that at all. And in fact, it doesn't move either when you get into your mechanisms class. That speed there will be 0. The RPMs on that, 0.
I'm just having a hard time with it because, like, when you go to break a bolt,
Mhm.
the bolt actually does the shear stress does cause a fracture. Is it just breaking along the threads? Is that basically what's happening? Because when you break a bolt, it's just it's straight across. You don't see any kind of elevation to it unless it's along the thread. I don't understand.
I mean, you can break a shaft anywhere. It doesn't necessarily have to be at the now. In your case of your bolt, it's more than likely it's going to break. But I've sheared bolts off that I haven't actually sheared them at the thread. Yeah, you can do that. Now, there's something else that made that happen. It might have been rusty, or it might have had a nick in it, something like that.
Because
But
I just don't understand how, like, right at the center, there's nothing there though. It's just like theoretically void of.
well, okay. So what was that calculation? Force times distance.
Well, I understand distance is 0, therefore it's 0, but that's not 100% true, is it? Because you can't.
Well,
There's always going to be something there, right?
if you could find 0, in theory, it's true. In reality, maybe not so much. Because you can't. It's just like making something perfect.
Right.
You can't make something perfect. I don't care what anybody says. Other than, I mean, my mom made me, but other than that, Sorry, couldn't resist. So, yeah, if you could.
If you had an air bubble in the casting or something, that would be its point of failure way before season 0 or something. So
Well, but in theory, yeah, right at the center, there's not going to be a movement. But again, you can't really measure right at the center. I mean, how can you get that small? But in theory, yes. But in reality, not so much. It's just, you can't build a machine that will get that minute. I mean, even your electron microscopes and stuff are not that good, no matter what any scientist tells you. There's always going to be an error somewhere in there. So, in theory, yes, 0. In reality, not so much. Okay? What else about that? Let's see, what else here do we need to say on that? So again, I think I said the shear stress developed in the torsionally loaded circular shaft is proportional to the distance from the longitudinal axis of the member, and the stress equals 0 at the axis and varies linearly to a maximum at the outer surface, which is what that picture depicts for you. Okay? Now the torque equation, if you look on page 251, if you're wanting to find torque, you take the torque is equal to the shear stress times J. Well, what's J? That's the polar moment of inertia. And note, you will be able to find that on the back cover of your book. Okay. Divided by C, which is the radial distance from the centroidal longitudinal axis to the outer surface, or to wherever you're trying to find that value. So that's where C here, okay, this C right here, you could actually, if you weren't trying to find it out at the outer surface for some reason, you were trying to find it somewhere in between, you just have to adjust that C, wouldn't you? And you should be able to find that torque value, or that, the torque value anywhere within the confines of that radius. Okay, so I need to say more about that? Just, you're going to have that equation handy, right? If you want to find torque, you're going to hopefully be able to use that equation right there. Now, what else? You'd have to know what the shear stress was, right? So you might have to calculate that first. I think we did something like that in that last quiz. You had to do this before you could do that on a couple of those problems. So keep that in mind. Also note that the shear stress, if you don't know that, but you know the torque, and you know the radius, and you know the polar moment of inertia, you can rearrange that calculation to get the shear stress, can't you? Well, why would that be important? Aren't you given shear ultimate, or in this case, proportional limits for shear and such on the properties back in the back of the book? So we have to make sure, if we know what the torque value is, we have to make sure we pick the right material and maybe even the right size to be able to overcome that torque value to resist that internally. So we have to work with different things, as we go along here. And that's what it said, that, remember, that relationship between the stress, the, what all was it? Go back to my notes now. Develop the relationship between the torsional shear stress, the torque, and the material physical properties. So that's where these calculations are going to pay off for us. To find the max resisting torque, or the allowable torque, we can rearrange that again. And note that is equation 12.3. So that last equation to find the shear stress, if you know those others, is 12.2. 12.3, if we want to find the max resisting torque or the allowable torque, we'll take the allowable shear stress that would be given in the charts, times the polar moment of inertia divided by that radius value. Okay. Note too that the maximum torque this is the maximum torque without exceeding the ultimate shear strength or allowable shear stress, and that would be the upper limit. In other words, you couldn't put any more on it than that based on what type of material you picked and so on. So that's what you're looking for there. Let's see. Now I've got the next chart I've got here is, let's see, do we need to do example? Nope, I'm sorry, we still got some more here. So note, for design of solid circular shafts, we can use equation 12.3 rewritten. So if you need to find out what the polar moment of inertia is, that's the equation that's, at the top of the, where did I find that? Well, yeah, this just, if you're trying to find the diameter, required diameter, they're developing that calculation. If you want to find the required polar moment of inertia, you take the torque times the C value and divide that by the allowable shear stress. Then if you had a solid shaft, note that the C value is the diameter divided by 2. And that's then you come up with the second equation there for the polar moment of inertia, which is pi times the diameter cubed divided by 32. And then if you set those equal to each other, you have pi times the diameter to the 4th divided by 32 equals the torque times the C value, which was D divided by 2, divided by the allowable shear stress. Well, if you rearrange that, the required diameter is the cube root of 16 times the torque divided by pi times that allowable shear stress. And that will tell you the diameter of the shaft that you need for a particular project. Okay? Now note down there in that table 12.2, there's typical increments that you can buy if you buy the shaft material that you're dealing with. So for a half inch up to 2.5 inches, they're saying you'll be able to buy that in increments of a 1/16 of an inch. When you go to 2 5/8 to 4, then you're not going to get them in 1/16 of an inch. You're going to get them in 1/8 of an inch. So what you would have to do is, if you had calculated, let's say you calculated the diameter at 2.48. Okay, so that's just a little bit under 2.5, right? But it's more than 2.4375, which would be 2 7/16, right? Well, you wouldn't want to buy the 2 7/16 diameter shaft. You'd want to go to the 2.5. So I think that's what's pertinent about that table. You're only going to be able to get it in increments of a 1/16 of an inch. So if it's somewhere between 2 7/16 and 2.5, you need to step up to the 2.5. That's what, or you could have your machinist turn it down to 2.48. Really, you want to do that work? Because then you're probably going to have to order a special pulley to put on it, because the pulleys tend to match the shafts. So not exactly. Actually, the pulley diameter might be 2.48, and then you have to press it on. It wouldn't be quite that big or that small, but you can press those on. Okay. What else there? We're almost out of time. Not quite. Example 2.12 or 12.2. Calculate the allowable torque that can be applied to a circular shaft. The allowable. That's interesting. The allowable shear stress is 83 megapascals. Assume the shaft is solid and has a 150 millimeter diameter. Well, now we're starting to find out some information. Assume the shaft is, that's for example A. For B, assume the shaft is hollow and has an outside diameter of 150 and an inside of 125. So for the first one, solid shaft, this will be pretty easy. The polar moment of inertia equals pi times the diameter, which was 150 millimeters, raised to the 4th power divided by 2. So the polar moment of inertia is 49.7 times 10 to the 6th millimeters to the 4th. Remember, it's a moment of inertia, right? So we get back into that situation. Now, continuing on, calculate the allowable torque. Well, the allowable torque was the allowable shear stress times the polar moment of inertia divided by C. Well, let's see. Did they give us the allowable? They did give us the allowable shear stress was 83 megapascals. So that's the same thing as 83 newtons per millimeter squared times the polar moment of inertia, which we just calculated. And then the C value, I think they gave us that. It was 75 millimeters was the, well, actually that's the radius, isn't it? 150 millimeter, yeah, so C is a radial value. So you just take the diameter divided by 2.
Question, so your answer is 55 times 10 to the 6 Newton meters,
Mm-hmm.
and then they just changed it to kilonewton meters. I thought kilo was 10 to the third. How did it go from 10 to the 6 to kilo?
Because it's Newton millimeters, not Newton meters.
Oh, yeah, Newton millimeters, sorry, yeah, all right, never mind.
Yeah, they changed both of them on
Yeah,
you
they
there.
changed both of them, yeah.
Yep. Okay. So, and basically all you're doing here is plugging numbers in. You just have to figure out exactly which number you need to plug in and where you need to plug it in. So, I would expect this test to be even better. So for the hollow shaft now, it's a little bit different. Note, and some people did this on the temperature thing. You tried to do like 0.030 over each one of those temperatures, and that wasn't quite right. You couldn't do that. So same thing on this. You don't want to, if you want to find that polar moment of inertia, note that they're taking the outside diameter minus the inside diameter and raising that to the fourth. Actually, they're taking each one of them and raising them to the fourth power.
You're saying it's kind of like what I did on that homework where I just, on the brass, like I said, that piece of electric kind of solid steel core. And then
Yeah, you tried to
around
subtract the areas.
Yeah,
Yeah, or subtract the diameters and then
yeah.
then do the area, and that, yeah, you can't do that. And the same thing here. Don't do that here either. Okay, so put those numbers in, raise them to the fourth power, and subtract the inside from the outside, and then multiply that by pi, and then divide by 32, and you've got the polar moment of inertia. It shows up as 25.7 times 10 to the 6 millimeters to the fourth. Then the allowable torque. Again, we're using the same type of thing there. 83 newtons per millimeter squared times the 25.7 times 10 to the 6 millimeters to the fourth, which was the polar moment, and divide that by that 75 millimeters again. And that's that's the max out at the end, isn't it? That's why you have to use the 75 there. Okay? Because it's like, well, wait a minute. Why wouldn't I use the inside diameter, and divide that by 2? Well, you're trying to find the max, and the max is out at the outside diameter, isn't it? Make sense? So that's why you use the 75 there. Well, let's see. Example 12.3. Calculate the maximum shear stress developed in a circular steel shaft when subjected to a torque of 95,000 pounds-inches. Assume the shaft is solid with a 4-inch diameter for the first one. Okay, so we got the solid shaft. We look and we find the polar moment of inertia. It's pi times 4 raised to the fourth power divided by 32. So we had 25.1 inches to the fourth. We take that, substitute it in. Now the equation this time is the shear, the torsional shear is equal to the torque times the C value, which is that radial value, right, divided by the polar moment of inertia. So we've got the 95,000 pounds-inches we were given. The C value is 2. Why is that 2? Because the diameter is 4, right? So the C value is the radius. And then we figured out what the polar moment of inertia was. It was 25.1 inches to the fourth. So we punched those numbers in, and we should find out that Max shear stress is 7,570 pounds per square inch. So that would be a number we'd have to go back and make sure that, you know, we were below what that would be for that material. Let's see, now the second part of that, you've got a hollow shaft and the outside diameter is 4, the inside diameter is 2. So again, polar moment of inertia, just take that outside number of 4 to the 4th power minus the 2, which is the inner diameter, to the 4th power, multiply that by pi, and then divide the whole thing by 32. Max shear stress is basically, we're doing the same thing here. The only number that changes is the polar moment of inertia, because it's still a 4-inch diameter outside. So that number, you know, nothing really. The only way that number is going to change is if we said, well, the diameter is 3 instead of 4. Then your number at the bottom, that 2 would then be 1.5, wouldn't it? Is the only thing there. And let's see, what else does it say there now? Oh, that number ended up being 8,050 psi. Now it does say the shear stress varies linearly from 0 at the longitudinal center of the shaft to 80-50 at the outer surface. Shear stress at the inner surface can then be calculated by the proportion. So in other words, there's the inner surface, they're talking about the ID, aren't they? The inner diameter, that is the inner surface. So it's 8,500 divided by 1/2, because the 2 is half of the 4, isn't it? So there's 4,025 psi max shear stress going on the inside of that pipe. Example 12.4, calculate the required diameter of the solid circular shaft, steel shaft, that must resist a torque of 20 kilonewtons per kilonewton meters. The allowable shear stress in the shaft is 83 megapascal. Select the shaft diameter to use. Okay, so note it says the torque is 20 kilonewton meters, and they're changing that to newton meters. 20 times 10 to the 3rd. That's kind of where you were at earlier, Jeff. Yeah. Okay. Then the allowable shear stress, 83 megapascals. They changed that to newtons per meter squared. So and they really didn't change anything other than the units essentially there, right? But they want to get them on the same. So the required diameter is a cube root of 16 times the torque. We were given the torque, right? 20 times 10 to the 3rd newton meters. Divided by pi times the allowable shear. Excuse me. The allowable shear stress was 83 times 10 to the 6 newtons per meter squared. You know what, that would be a good thing that you would probably want to punch those numbers into your calculator and make sure you can get that value. It comes out as 0.1071 meters, and then they just change that to millimeters, which is just moving your decimal point 3 places to the right. So 107 millimeters diameter. Now, but then the last part of that said select a shaft diameter to use. See, if you were given that on a test, you would still have to do that, and that would be one I would probably not look the other way on. Okay, so for that shaft, then the next increment up would be a 110 millimeter shaft, and you would want to go up, but you wouldn't want to go down if it was 105. Because you'd screw up your shear, wouldn't you? You wouldn't be meeting that value. Okay, there are a couple more examples there. Well, obviously we're not going to get to those today, but and I haven't looked over the homework problems to decide what to give you. So what I will do is I will go back to my office look those up and post it, so you'll know, what you ought to probably look over between now and Friday. Fair enough?